In this lecture, we'll start talking about solving non-homogeneous differential equations using the method of undetermined coefficients, specifically the superposition approach. Before we get started with the superposition approach, here's a couple of things to practice with or warm up with. Find the derivative of the following functions. So first, x cubed plus 4x squared minus 18x. Second, the sine of x plus e to the 4x. And third, x to the fourth plus 2x e to the minus x. Pause the video and see if you can find these derivatives. All right, so if we want to find these derivatives for the first one, we're going to get 3x squared plus 8x minus 18. For the second one, we get cosine x plus 4e to the 4x. And for the third one, we get negative x to the fourth plus 4x cubed minus 2x plus 2 times e to the minus x. Now notice that the form of the derivative matches the form of the function we started with. So for problem 1, we had a polynomial function, and when we took the derivative, we still have a polynomial function. In problem 2, we had a trig function, specifically sine or cosine, plus an exponential, and our derivative also takes the form of a trig function plus an exponential. In 3, we had the product of a polynomial times an exponential, and the derivative wound up being a product of a polynomial times an exponential. All right, so we're going to use this idea, we're going to use this kind of result to motivate the superposition approach to the method of undetermined coefficients. All right, so to solve a non-homogeneous ODE using the undetermined coefficients method, the first thing that we're going to do is we're going to solve the homogeneous ODE. That's going to give us what's called the complementary function, which we write as y sub c. Then we're going to pick a generic form of g of x, and we're going to assume that that is our yp. So that kind of goes back to what we did on the previous slide. If g of x is a quadratic function, then we're going to assume that yp is a quadratic function as well. Because in order for a combination of derivatives, which is essentially what a differential equation is, to give us a quadratic, then the function that was plugged in has to be some sort of polynomial. Right? So then we're going to take that yp, we're going to take it and its derivatives, we'll plug them into the ODE and we'll simplify. And then we're going to solve our undetermined coefficients for A, B, C, D, however many we have. All right, and if your textbook covers the method of undetermined coefficients with the superposition approach, there's often a list of generic particular solutions in your book. So you may want to check your book and see if you can find that table. That may be helpful in choosing that generic form of g of x when we're assuming what yp is. All right, so we have two cases when we're solving a non-homogeneous ODE using the superposition approach to the method of undetermined coefficients. The first is that no function in our particular solution, so no function in yp, is a solution to the homogeneous DE. So that says there are no terms in yp that are also in yc. So let's look at an example of this. We want to solve y double prime plus y prime minus 6y equals 2x. So again, the first thing that we do when we're solving a non-homogeneous differential equation is we start by solving the corresponding homogeneous differential equation. So we'll find our auxiliary equation. That'll be m squared plus m minus 6 equals 0. We can factor that out to be m plus 3 times m minus 2 equals 0. So m will be negative 3 or positive 2. And that means that our complementary function, y sub c, is going to be c1 e to the negative 3x plus c2 e to the 2x. Now we need to go and find our particular solution, yp. So since our right-hand side g of x is equal to 2x, 2x is a linear function. So we're going to assume that yp is also a linear function. The generic form of a linear function is ax plus b. So we assume that yp is ax plus b. We're going to take yp and its derivatives. So yp is ax plus b. yp prime is equal to a, and y double prime is equal to 0. And we'll plug those into our differential equation. So if y double prime plus y prime minus 6y has to equal 2x, that means 0 plus a minus 6 times ax plus b has to equal 2x. And if we simplify that, distribute that negative 6 to get rid of those parentheses, we'll get a minus 6ax minus 6b equals 2x. All right, once we get to this point in the problem, after we've simplified and we have these two sides of the equation equal to each other, if these two sides of the equation are truly equal, then that means that each term, or the terms on each side, have to be equal. So what we're going to do now is we're going to equate our coefficients to determine what a and b are. So to equate our coefficients, we're basically going to look at the terms on each side. So if we start with our x terms, on the left-hand side I have negative 6ax, and on the right-hand side I have 2x. So again, if this statement is true, if these two expressions are truly equal, that means that those coefficients have to be the same. So negative 6a has to equal 2. And then we look at our constant terms. On the left-hand side, we have a minus 6b. On the right-hand side, we don't have a constant term, so we'll assume that's 0. So that means a minus 6b has to equal 0. This gives us a system of two equations with two unknowns, which we can solve. So looking at that first equation, if negative 6a is equal to 2, well, that means a has to equal negative 1/3. We can take that a equals negative 1/3 and plug it into the second equation. So negative 1/3 minus 6b equals 0. If we solve that, we'll get b equals a negative 1/18. So that means that our particular solution, yp, is going to be negative 1/3 x minus 1/18. The final step is to form our overall solution by putting our complementary function, yc, and our particular solution, yp, together. So y equals yc plus yp. For this problem, that's going to give us y equals c1e to the negative 3x plus c2e to the 2x minus 1/3 x minus 1/18. All right, let's look at a second example. So y double prime plus 2y prime equals 2x plus 5 minus e to the negative 2x. So if we go through the process, again, the first thing we're going to do is we're going to solve the homogeneous part of the equation. So m squared plus 2m equals 0. That means m times m plus 2 equals 0. So m equals 0, or m equals negative 2. So that gives us the complementary function, yc equals c1 e to the 0x, which would just be c1, plus c2 e to the negative 2x. Next, we turn our attention to the particular solution. So to find yp, we look at our right-hand side. G of x is equal to 2x plus 5 minus e to the negative 2x. This is a linear function minus an exponential. So we can think of this as the sum of a linear function and an exponential function. So we're going to let yp equal a to the x plus b plus c e to the negative 2x. All right, so again, we're going to take those derivatives. So yp equals ax plus b, c plus c e to the negative 2x. Yp prime equals a minus 2c e to the negative 2x. And yp double prime equals 4c e to the negative 2x. When we plug those into our differential equation, we get 4c e to the negative 2x plus 2 times a minus 2c e to the negative 2x equals 2x plus 5 minus e to the negative 2x. So we can simplify 4c e to the negative 2x plus 2a minus 4c e to the negative 2x equals 2x plus 5 minus e to the negative 2x. Now when we look at this solution, so we've simplified, we can equate our coefficients. If we look at our constant coefficients, we have 2a on the left, and we have 5 on the right, so 2a has to equal 5. If we look at our exponentials, we have 4c minus 4c on the left, and we have -1 on the right. So that's going to tell us that 0 equals -1. Well, 0 doesn't equal -1. And additionally, if I look at this, there's no way for us to figure out what gave us the 2x. So we've made a mistake. Somewhere. I've wasted 2.5 minutes of your time because there's a mistake in the problem. So let's talk about where that mistake is so that you'll know how to avoid making this mistake when you're solving these problems in the future. All right, so remember when we started talking about these, we said that there was a case 1. There's also a case 2. So case 2 says that the function of your assumed particular solution is also a solution to yc. So what happens with case 2 is if any yp duplicates terms in yc, then that yp has to be multiplied by x to the n, where n is the smallest number that would remove the duplication. All right, so let's go back to our example. So this was our differential equation, and we had yc equals c1 plus c2 e to the -2x. Right? In our previous attempt where we made our mistake, we assumed that yp equals ax plus b plus ce to the -2x. But notice here that the b term, that's just a constant, that takes the same form as c1 in our complementary function. And since c1 is part of the complementary function, we know that that's going to give us 0. So that repetition is going to cause a problem. Additionally, this last term, ce to the -2x, takes the same form as c2 e to the -2x. So that's another repetition that's also going to cause a problem. So what we do is we multiply all of these terms that have repetitions by x. So if we do that, we get ax plus bx plus cx e to the -2x. Well, now ax and bx have the same form, so we need to multiply one of them by x one more time. So we would get ax squared plus bx plus cx e to the -2x. So now when I look at my yp and my yc, there are no repeated terms. Everything is distinctly different. So now I can proceed with the problem. So yp equals ax squared plus bx plus cx e to the -2x. Again, we'll take our derivatives. So yp prime will be 2ax plus b plus c e to the -2x minus 2cx e to the -2x. Remember, we have to use the product rule on that last term. And then yp double prime will be 2a minus 4c e to the -2x plus 4cx e to the -2x. We'll take those derivatives and we'll plug them into our differential equation. So that's going to give us 2a minus 4c e to the -2x plus 4cx e to the -2x. If I do 2 times y prime, I'll get plus 4ax plus 2b plus 2c e to the -2x minus 4cx e to the -2x. And that should equal our right-hand side, 2x plus 5 minus e to the -2x. Now that we've simplified everything, we can equate our coefficients. So let's start with our x e to the -2x terms. On the left-hand side, we have 4c minus 4c. And on the right-hand side, we don't have one. So we get 4c minus 4c equals 0, which is true. If we go to our constant terms, we have 2a plus 2b on the left, and we have 5 on the right. So 2a plus 2b has to equal 5. If we look at our x terms, 4a on the left and 2 on the right, so 4a has to equal 2. And if we look at our e to the -2x terms, we have negative 4c plus 2c on the left, and we have a negative e to the -2x on the right. So looking at those coefficients, that means negative 4c plus 2c has to equal a -1. So if we simplify that, that'll give us negative 2c equals -1. So this gives us a system of 3 equations with 3 unknowns. If negative 2c equals -1, that means c has to equal 1/2. If 4a equals 2, that means that a is also 1/2. And we can take that a equals 1/2 and plug it into the first equation to figure out what b is. So if we plug a equals 1/2 in, we can solve and we get b equals 2. So that means that yp is going to be 1/2 x squared plus 2x plus 1/2 x e to the minus 2x. And our overall solution will be c1 plus c2 e to the negative 2x plus 1/2 x squared plus 2x plus 1/2 x e to the negative 2x. All right, let's look at one final example. So this time we have y triple prime minus 2y double prime minus 4y prime plus 8y equals 6x e to the 2x. Again, we always start by finding our complementary function. So we solve the homogeneous part of this differential equation. So m cubed minus 2m squared minus 4m plus 8 equals 0. We can factor this by grouping. So that's m squared times n minus 2 minus 4 times m minus 2. So that gives us m squared minus 4 times m minus 2. So we get m equals negative 2, positive 2, and positive 2. That means that our complementary function yc is going to be c1 e to the negative 2x plus c2 e to the positive 2x plus c3x e to the 2x. All right, now that we have our complementary function, we can focus on finding the particular solution. So for our particular solution, g of x is equal to 6x e to the 2x. That's a linear function times an exponential. So we're going to assume that yp takes the same form. So yp equals ax plus b times e to the 2x. All right. Now before we continue with this, let's check and make sure that there's no repetition. All right. So if I look at these terms, I have ax e to the 2x and I have b e to the 2x. Well, those match up with two of the terms in my yc. So I have to remove that repetition before I can continue with my yp. Otherwise, I'm going to wind up wasting my time like we did on that previous example. So to remove the repetition, we'll multiply by x. So we get ax squared plus bx e to the 2x. Well, that bx e to the 2x, that's still of the same form of the last term of yc. So we'll multiply by x again. And so we wind up with yp equals ax cubed plus bx squared e to the 2x. Now that we found a particular solution, or the form of a particular solution rather, that doesn't have any overlap, doesn't have any repetition with our complementary function, we can proceed to take its derivatives and plug it into the differential equation. So if we take our derivatives of yp equals ax cubed plus bx squared e to the 2x, we'll get yp prime equals 2ax cubed plus 3a plus 2b times x squared plus 2bx e to the 2x. Yp double prime is going to equal 4ax cubed plus 12a plus 4b times x squared plus 6a plus 8b times x plus 2b times e to the 2x. And then y triple prime will be 8ax cubed plus 36a plus 8b times x squared plus 36a plus 24b times x plus 6a plus 12b e to the 2x. All right, so we have our derivatives and our function. We're going to plug those into our differential equation. All right, so our differential equation says y triple prime minus 2y double prime minus 4y prime plus 8y equals 6x e to the 2x. So I'm going to put those in. I'm going to write this vertically just to save space, excuse me. Right? So if I take my differential equation, I have y triple prime. So that was 8ax cubed plus 36ax squared plus 8bx squared plus 36ax plus 24bx plus 6a plus 12b, and all of those terms were multiplied by e to the 2x. I do minus 2y double prime, so I'll go ahead and multiply that by what we had for the second derivative. That'll give us negative 8ax cubed minus 24ax squared minus 8bx squared minus 12ax minus 16bx minus 4b, again all times e to the 2x. Minus 4y prime will give us negative 8ax cubed minus 12ax squared minus 8bx squared minus 8bx, all times e to the 2x. And then 8y gives us 8ax cubed plus 8bx squared times e to the 2x. Now I've written it like this kind of in columns to make it easier to add them together. So when we add all of these together, we'll see that the ax cubed terms will all cancel out. The ax squared terms will all cancel out. The bx squared terms all cancel out. 36ax minus 12ax gives us 24ax e to the 2x. 24bx minus 16bx minus 8bx, those cancel out. 6a is by itself, so I get 6a. And then 12 minus 4b gives me 8b, so I get 24ax e to the 2x plus 6 plus 8b e to the 2x equals 6x e to the 2x. Now that I've gone through that process and I've simplified, I can equate my coefficients. So if I look at my x e to the 2x terms, I have 24a on the left and I have 6 on the right. So 24a equals 6. If I look at my e to the 2x terms, I have 6a plus 8b on the left, and I don't have 1 on the right, so 6a plus 8b has to equal 0. We can solve this system of equations. From our first equation, a has to be 1/4, and if we plug that into the second equation and solve, we get b equals negative 3 over 16. All right, so we can plug those in to get our yp. Yp is going to be 1/4 x cubed minus 3/16 x squared times e to the 2x. And then we'll put it all together to get our overall solution. So y equals c1 e to the negative 2x plus c2 e to the 2x plus c3x e to the 2x plus 1/4 x cubed e to the 2x minus 3/16 x squared e to the 2x. So that'll be the solution to our differential equation.